Today we shall study about limitation of Ohm's law in current electricity. Although Ohm's law has been found valid over a large class of materials, there do exist materials and devices used in electric circuit where the proportionality of V and I does not hold. The deviations broadly are one or more of the following types. As shown in the figure 1, graph between potential difference and the current. V is said to be proportional to I in figure 1. The relation between V and I depends on the sign of V. In other words, if I is current for a certain V, then reversing the direction of V, keeping its magnitude fixed, does not produce a current of the same magnitude as I in the opposite direction in figure 2. This happens, for example, in a diode. The relation between V and I is not unique. It means there is more than one value of V for the same current I in figure 3. A material exhibiting such behavior is gallium arsenide. A materials and devices not obeying Ohm's law in the form of equation V barabar Ri are actually widely used in electronic circuits. Resistivity of various materials. The resistivity of various common materials are listed in table below as shown in the figure. Shown in the table. Conductors are silver, copper, aluminum, tungsten, iron, platinum, mercury, nichrome. The value of resistivity is given and the value of semiconductor for resistivity and for insulator are also given. Now the materials. Now the materials are classified as conductors, semiconductors and insulators. Depending on their resistivity, in an increasing order of their values, metals have low resistivity in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. At the other end are insulators like ceramic, rubber and plastic having resistivity 10 to the power 8 times greater than metals or more. In between the two are semiconductors. These have resistivity characteristically decreasing with a rise in temperature. The resistivities of semiconductors are also affected by presence of a small amount of impurity. This last feature is exploited in use of semiconductors for electronic devices. Commercially produced resistors for domestic use or in laboratories are of two major types. First is wire-bound resistors, second is carbon resistors. The wire-bound resistors are made by binding the wire of an alloy. It means manganese, tungsten, nichrome or similar ones. The choice of these materials is dictated mostly by the fact that their resistivities are relatively insensitive to temperature. These resistances are typically in the range of a fraction of an ohm to a few hundred ohms. Resistors in the higher range are made mostly from carbon. Carbon resistors are compact, inexpensive and thus find extensive use in electronic circuits. Carbon resistors are small in size and hence their values are given using a color code as shown in the table for the resistors color code: black, brown, red, orange, yellow, green, blue, violet, grey, white, gold, silver, no color. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. and the multiplier is 1 guna 10 to the power 1, 10 to the power 2, 10 to the power 9. Tolerance 5, 10, 20. The resistors have a set. The resistors have a set of coaxial colored rings on them. The first two bands from the end indicate the first two significant figures of the resistance in ohms. The third band indicates the decimal multiplier. The last band stands for tolerance or possible variation. In percentage, about the indicated value, a tolerance, for example, if the four colors are orange, blue, yellow and gold, the resistance value is 36 × 10 to the power 4 ohm with a tolerance of 5%. As shown in the figure for color code. Now the temperature coefficient, temperature dependence of resistivity. The resistivity of material is found to be dependent on the temperature. Different materials do not exhibit the same dependence on temperature over a limited range of temperatures, that is, not too large. The resistivity of metallic conductor is approximately given by ρ t barabar ρ0 into 1 plus alpha t minus T0, where ρ t is the resistivity at temperature T and ρ0 is the same at reference temperature T0. Alpha is called the temperature coefficient of resistivity and the dimension of alpha is temperature -1. For metals, alpha is positive and values of alpha for some metals at T0 barabar 0 degrees C. The graph of ρ t plotted against T would be a straight line at temperatures much lower than 0 degrees C. The graph deviates considerably from a straight line. Graph between resistivity and temperature T is shown as a hyperbola, and the graph between resistivity and temperature shown as a straight line. For nichrome as a function of absolute temperature. First, the resistivity of copper is a function of temperature, and the third is parabolic. Temperature dependence of resistivity for typical semiconductor. The resistance of metal would change very little with temperature. The resistivity of semiconductor decreases with increasing temperature. So, resistivity बराबर 1/, conductivity बराबर m/n square tau. इसलिए rho is inversely proportional to 1/n. So, tau decreases with increasing in temperature. Therefore, the variation in temperature do not vary more for metal, but variation in temperature would increase the value of resistivity in semiconductor and insulation.